As we had said in the last class, in today's program, we are first going to discuss about some, not really discuss, rather I am going to give you homework. So, I am going to give you some problems for you to solve using the Karush-Kuntakar conditions or the Fridtjohn conditions that we have learnt here. I want to remind that we would call a Fridtjohn conditions as a Karush-Kuntakar conditions or Kuntakar conditions if all the Fridtjohn multipliers associated with it is normal. Now, such a thing would happen if the Mangasarian Fromovich constant qualification holds, that is what we have seen in the last class. And also we have spoken about the fact that every linear program, we have proved that for every linear programming problem, all the multipliers are normal multipliers, all the John multipliers are normal. So, now we are going to give some homework, especially I have picked them up from the book Foundations of Optimization by Osman Guler, and let me list down the homeworks. And after that we would start our study of quasi-Newton methods, which I have said mimics, or rather sorry, which I have said needs to have, one needs to have an understanding of constant optimization in order to really understand the convergence analysis of the quasi-Newton method. This is very important in algorithms, even if we do not run them and do not try to put them on the computer and check how they are behaving, which I possibly do not do myself, because I am a theoretician. So, it is important to have an understanding, at least mathematically, how the sequence of iterates that you would generate through an algorithm behaves, and many computer scientists would agree, then especially algorithm specialists, that they might not have really sat down on the machine, but somebody else have done the programming and trying to see how the things behave. But to mathematically predict what would happen to a sequence of points that are generated by some algorithms, that process is called the convergence analysis of that algorithm, and those things are very important and very useful when you are really talking about an algorithm. That we have learned such things when you are speaking about conjugate gradient methods and all those things. A similar sort of approach would be taken in the case of the quasi-Newton method. So, okay, let us look at our first homework, which says so x is in R and each xi is in R, such that so this is called separable programming. The full function can be written as a sum of some other functions. Obviously, I have here so if you have a function of two variables only, that is n equal to 2, then the feasible set is easy to draw. So, this is 1 and 0 and this is 0 and 1, and we draw it here. Now, the feasible set would look like this. The interesting fact now is, how do we now start solving this problem? Possibly we would assume that there is a solution. How will you first assume that there is a solution? Now, the feasible set here, the set C, is sort of all x in Rn for which all the components are non-negative, that it is in Rn plus, and then oh sorry, I made a mistake. I think if that was less than equal to 1. So, this is the, sorry, I did it. So, this is my feasible set C, this line passing through 1 0 and 0 1 and remaining only in the non-negative part. When n is 2, this is your C. So, first thing to observe that this set C is a convex compact set in R2. So, this if we assume all the Fi's are differentiable, then you are assuming all of these are continuous, and hence you are telling that this is my feasible set which is compact, these are continuous functions because they are differentiable, and hence there will be a solution. Now, where will the solution lie is a different issue, this or it depends on the Fi's. So, suppose I do not know the Fi, I will try to at least have a qualitative feeling about the solution by applying the Karush-Kuhn-Tucker condition. So, apply KKT. Now, here one important piece of our learning would come into play. This constant and all these constants here are linear. So, the Karush-Kuhn-Tucker condition automatically holds, means all the John multipliers associated with this problem would always remain to be normal. Now, it is very important to have a little bit of look at the history of this problem. This is not a 20th century or post World War II problem. It is a problem which was known to the American physicist J.W. Gibbs, one of the greatest contributors in the field of thermodynamics in the 19th century. So, this problem that we see here was related to thermodynamics, and it came up in the study carried out by J.W. Gibbs in the 19th century. So, here you have a 19th century problem to be solved by 20th century method. So, I leave this problem to you to have a look at. Now, I will give you two different problems, question number 2 and question number 3. They will be slightly different, and it is again important for you to figure out the solution. Now, it is much more easier because here, but you have to guarantee that what you get are solutions, because we have not yet spoken about second order conditions. So, we cannot say that we will apply the second order conditions. Just by applying the Karush-Kuhn-Tucker conditions and getting some information, can you from the problem structure say what is your solution? That will be the question. So, there is a function problem in 3 dimensions, right, and subject to now change the problem slightly to here you have to proceed by applying we may proceed now by applying what we have learned. Now, the question is, do we really have to look at the Karush-Kuhn-Tucker Fridtjohn condition first and then look at the Karush-Kuhn-Tucker conditions? That is the question. So, when you are trying to solve this question, this is the first question should arise in your mind. How is this problem, right, in the sense that basically it is telling that x y is equal to 1. So, what does it mean? Does it mean that I am able to solve this problem, yes or no? Now, how do I know that there would be a global minimizer of this problem? How do I know that there is a global minimizer of this problem? Once these two are known, then I can start taking some steps to solve them. Here we need the idea of coercivity, I have not spoken much about it, or maybe have not spoken at all. So, to know that these problems have a solution needs coercivity, because these things do not represent compact sets in R3. They both represents closed sets in R3, but they do not represent compact sets. So, here would come the notion of coercivity, or it is or is also called the first order growth condition. So, it is how the function grows as the norm of the decision vector x becomes larger and larger. Decision vector x y z here in this case, or x vector x 1 x 2 x n becomes larger and larger. Now, so if you are considering a function R n to R and you are considering a closed set C, f is coercive on C if f of x, the limit of this becomes plus infinity whenever norm of x goes to infinity with x remaining inside C. Such a thing would not happen if set S is bounded, norm x is bounded. If the set C is bounded, you cannot have norm x going to plus infinity, of course, with x remaining in C. So, these things become helpful when the set C is actually not compact, not bounded at least. So, these facts then become helpful. So, if this is there, so if f is continuous and C is closed and f is coercive on C, then there exists a global minimizer of f on C. Now, I would leave you as an exercise first that this set, that the set C x y z belonging to R3 with to 1 and this set C here now your first step would be to show there is a closed set. So, I am just giving you certain hints so that you are enthused to take up your pen and paper and solve these problems. Okay. So, once you have that these two, then I would fairly be happy that I have got the first step, because it is very important to see that this function as x, y and z, the norm of these as these quantities go towards infinity, this whole function would go towards infinity. So, the coercivity condition is taken over. So, I am guaranteed that these have a global minimizer. Now, how to decide whether these problems are having normal or not normal, right. Now, you see one of the, when you have just inequality constants, one of the conditions which will guarantee you always that there is a normal John multiplier is the linear independence of this inequality constant x y minus 1 equal to 0. But this linear independence of the gradient of the inequality at the solution. Now, you can observe that 0 0 cannot be an element of this set, because 0 0 is not equal to 1, 0 is not equal to 1. So, both x and y here cannot be 0, z could be 0, does not matter. So, here the gradient of say this is your h. So, let me put h in this case as x y z minus 1. So, gradient of x y and z is actually y, x and 0, and x and y both cannot be 0. So, this is a non-zero quantity, none of them are 0. So, which once this is non-zero quantity, which means this set is a linearly independent set trivially, and then hence that linear independence of the gradient at the solution always guarantees a normal multiplier. So, all multipliers are normal. Here also x, y, z can all, none of them can be 0. If one of them is 0, then this cannot be an element here, right. The solution cannot, the solution has the, so I need this only at the solution. So, at the solution point means x and y, none of them are 0 here. So, here the solution x, y, z, x bar, y bar, z bar is the solution, then x bar, y bar, z bar, none of them are equal to 0. In this case, so you have that grad of h. If I take this as my h now, x, y, z minus 1 equal to 0, then I will have here as and this is not a 0 vector. So, here also all John multipliers are normal. Okay. So, we have 3 problems, we have some information about the behavior of the function. So, you start applying the Karush-Kuntagar conditions and try to see what you can get from them. Okay. We go to another interesting problem from Goulet, which is pretty interesting by its solution, by its whole structure, and gives you a very nice answer, which will maybe one of the answers will be discussed. So, or maybe I will put them in the FAQs or in the notes. So, this is your function. So, objective function. So, x1 cube x2 cube, this is the same one, same sort of structure that we see in problem 1. This is your problem number 4, and here there are some interesting constraints. Summation xi is 0, does it, so some could be, some of the xi's are positive, some are negative, and all those things. Sum xi square is n. Okay, so now very important question is whether such a set of, whether we have any, here we cannot talk about coercivity because we have a cubing structure. So, with cube structure there is a, when something is going to minus infinity, some value of xi, because norm has to go to infinity. So, if xi is going to minus infinity, xi cube also goes to minus infinity. So, this is not a fair deal actually to talk about coercivity here. So, we have to decide by some other method. This is a continuous function. So, my feasible set C here okay. It is very important to note that this set is not only closed, but I would leave you again as homework to show that C is compact. Now, once you show that C is compact, you have actually told that there is already a solution to this problem. So, a solution to this problem exists. Now, consider this as G1x and consider this as G2x. So, I am now going to ask whether these are linearly independent. G2x means of course, this minus n, rather I should write like this. Whether these conditions are these constants are linearly independent solutions, if they are linearly independent at the solution, the gradient of this and this. If the gradient of this and this form a linearly independent set at the solution, then we are thoroughly sure that all the multipliers would be normal, and that is exactly the way we need to now proceed. Now, let us compute the gradient. This is and now, when are these linearly independent? When x is a multiple of E, when x is, so grad G1 not linearly independent, linearly dependent. Way to talk about it, we shall let grad G1 and grad G2 x, or so extra, suppose x is now the solution, or linearly dependent. Then only we cannot say whether we will always have a normal multiplier or an abnormal multiplier, we can have anything. We can have, we will obviously have one abnormal, but we can also have normal. So, let us first check whether this is true. So, in this particular case, let us observe that you have, so when would this happen? So, if x is equal to some lambda times E, then you will have these are to be linearly independent. So, if x is lambda times E, some lambda, then is such an x feasible? Now, if I look at summation x I, right, then this would be equal to lambda, but lambda cannot be 0, right. If x is 0, then lambda is of course 0, then it is satisfying. If x, but if all of the x cannot be 0, because then summation x I square cannot be equal to n, then because then n would be 0, which is not. So, which means x is not 0. So, all the lambdas, this lambda cannot be a 0 vector, E is not 0. So, this would not equal to 0. So, if x is equal to lambda E, now I am putting lambda now on lambda, this is lambda, 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 lambda. So, I am putting lambda in place of x i's, so which is violating the constant. So, any such thing with this thing cannot be feasible. This cannot be feasible. So, you see just from the problem conditions, we are being able to figure out whether all the John multipliers are normal or not. So, which means now we can simply apply what we will call the Kaggeri condition, right. So, now we will go to our next study, the quasi Newton method, and which we had been postponing for quite some time. In the next class.